and we're all tired. We'll be quick. This is an update primarily it's an update for the OpenCAPI Verification IP that we had been developing. And before that, I'll quickly go through a few slides about our products, how we do our products, and okay, so about 10 years back, we developed something called like a smart compiler, and we have a proprietary language in which we can encode a specification and enter into our compiler and in an executable format, and that can produce verification IP. So in SmartDV language, this is how we try to define a verification IP. Basically, irrespective of the user platform, the verification IP should be generatable, say for emulation, simulation, or for FPGA, post-silicon. We also have another version of the smart compiler that can actually generate digital design IPs, given the same specs. And that's how we can, get ahead of the market because we can be early adopters with protocols, say OpenCAPI, and we can create verification IP for OpenCAPI or be like say TileLink for RISC-V stuff, and get verification IP cranked out pretty quickly enough. So here's a statement that verification IP baselines the design ecosystems. So what I mean by that is that you have your test bench ready before even you do the design. So given those two block diagrams, one is for TileLink and one is for OpenCAPI. Once you have that infrastructure in place, you can replace any of those blocks with your design blocks, and you can run your test bench pretty quickly. So that's where critically fit in a verification IP in the design cycles, and I think that's very important and critical for design success. So this is a list of the verification IP that we have. Apparently, we are the largest provider in the world for different verification IP for different specifications. Feel free to browse our web at smartdv.com. So this is a brief slide for our synthesizable verification IPs. So we have we can generate verification IP versions which is SIM-XL compliant. So what that means is with a little, you can use the same APIs across simulation and emulation. Basically, moving from simulation to emulation is a breeze. It's pretty quickly. In the current market, existing solutions that you have from the big three vendors, they take a lot of time when you move from simulation to emulation. But because we support something like a very, SIM-XL compliant verification IP, what that means is this conversion, moving from platform to platform, from engine to engine, say simulation to emulation, is pretty quick. We also have verification IP for formal verification. I will not go in details of that. If you have questions, just feel free to ask me later or reach out to me if you need more information on that. And this is, so this library is somewhat new. We have, currently this library has some, for the serial protocols primarily, the SPMI, I2C kind of protocols. So you can do post-silicon level verification using these verification IPs. Basically, you can program our verification IP into FPGAs and can do post-silicon verification using this set of verification IPs. Okay, so now that was an overview on our product stuff, and this is now quickly jumping into the highlights of our OpenCAPI verification IP. That's where the highlights are. So our OpenCAPI verification IP is in the market, I think, about for a year now. We had been the early adopters. We had been working with a verification IP designer team, and over a year we have produced OpenCAPI verification IP that supports to the latest specification 4.0, which little off right now, work in progress for those 4 bullets. But other than that, we kind of cover the entire 4.0 specification today with our verification IP offering in the OpenCAPI. And it's proven by the early adopters. We cannot take the name. We have few early adopters with whom we have worked and matured, the spec and the verification IP together, being the early adopters. We provide the standard UVM verification IP blocks in the offering. We have our host and device modes of the verification IP, and we provide the passive monitoring of the bus, where also you can collect coverage. And also have a checker. So we call the scoreboard a checker. So for that for the data path verification on your bus. Any question on that? I think it's pretty clear, I guess. All right, so we implement the entire OpenCAPI layers, layer to layer, transaction layer, data link layer, PHY. And we provide debug at the layer boundaries within our verification IP. We basically do transaction logging at the boundary level, so you know what's going into a specific layer and what's coming out, and you can cross-verify. And as you know, at the same time, we have our data checker going. So together with that and the transaction logging, you can very easily do debugging at the layer level of the protocol. We support callbacks. You can do various things with the callbacks. Right now, we use callbacks for error injection, deletion, and we also provide some tasks that the user can modify for playing with the behavior of the error they inject in the design. In addition, you can do a backdoor stuff with the callbacks. There are standard methodologies for that. So here I saw in this block diagram, I saw a little inside our verification IP, how it's kind of architected. So each, say the host or the device, there are 2 ports. One is transmitter and one is receiver. And both has, and the transmitter works around a common FIFO. So that common FIFO is the interface of the user. So a UVM user will primarily be writing sequences to write into the FIFO. And the way our BFM, the host BFM will work is, if the training link, the link is up after the training, then it will look into the common FIFO, and if it's empty, then it will start sending idles frames, and once it sees that something is in the common FIFO, then it starts sending that over the link. And in the same manner, in the receiver end, you have a FIFO where the receiver puts the data package that's coming into the God FIFO. And then we have these states objects sitting there, and that primarily collects information from the bus, and that goes into our the monitor analysis ports, and that creates the database for the functional coverage. And this is something more on the debug. So we implement debug ports. So debug ports are primarily state variables from our BFMs within the verification IP. For example, for the training phase, we have a link training state variable. I'm not sure if it's very clear in the waveform that I saw there. So you basically track that state variable as the link progresses, and if certain sequence values that you can see within the link, that state variable, that debug port, is not correct, that's when you should see a assertion is firing. Basically a property that will be part of our protocol validation part of the monitor, and you should see a firing coming from there. So by firing, what I mean is it's a violation. And so in addition to that, we support a specific way of debugging the verification at the waveforms at waveform level. So we call it a SmartDV VIP debug, Smart VIP debug. And so that apparently what it does is it tabulates all the transactions that you drive into, drive from your master or from your device or from your host. And it can cross-reference between the transaction table and the waveform. So you can go back and forth. Also, at the same time, that protocol, that debugger, has the spec built into it. So it can show you, in ideal case, in case of a non-failure, how the waveform should look like. And in your application's case, how it is going wrong. So it can basically show the differences. So I have one slide on that later in the presentation, just so you have a pictorial view of it. And this is like writing a test, how we write a test in our VIP. It's pretty simple. For example, this is a test case that you write for training. So where you basically say that you want to do, first thing you have to do is what speed you want to work. So you can see that it's a 25 gigabit speed I have set in the SDVT configure. I think I could use this. Oh no. Thank you. Yeah, right there. And then you wait some time, and then after you set the command frame for doing the training for the host, and then you process that, and then after for the device you do the same thing, and then you process that. So this is the simplest way. This is a very simple way to do a training, done. And once you do that, then you can look at the logs. And what is the status of your training at some point. So for example, here at this specific time point, you have your transmit link training done at that point, and while the receive link is not done. So if you have retraining, so as you go, so you at some point you have both this training as done, and at that point basically you are done with your training. So this is what I was talking about, the Smart Verification IP debug. So you have a transaction table going there, and that transaction table can tell you if that transaction went okay or not. By bad and good, there is some status going on there, and then it also pops the waveforms, and you can cross-reference at certain time point when you take your cursor. You can go to the exact transaction over there. So and if something is bad, in that case, you can see your application where it's going wrong, cross-referencing, going back and forth on time there. And if you want to see what is the ideal case, then you can see your spec waveforms coming in another tab over there. And this is independent of simulator or emulator, so yeah, it's kind of like it works on a post-processing basis. So so any tool you may be using for your verification, this debugger will still work. This is, we call it Smart VIP debug. That will still work. Okay, so if you, we are industry proven. Like I said, that we have more than 100 customers, and out of the 10 top semiconductors, 7 are our customers. So feel free to reach out to us for any of your verification IP need, and also of course OpenCAPI. We have the verification IP out there in the market. So. Thank you.